We have mentioned pointers a few times now, so let's break down and understand what's happening under the hood. Pointers are a fundamental concept in many programming languages, including Go, and they are essential for writing efficient and powerful code. So, what exactly is a pointer? At its core, a pointer is a variable that stores the memory address of another variable. That's the key difference. Instead of holding a value like 10 or hello, it holds the location in your computer's memory where another value is stored. This allows for what we call indirect access. You can get a variable value not by using variable directly, but by going through the pointers that knows its address. In this diagram can show the visual representation. Let's walk through it. We have our simple Go code like x equal to 10, p equal to ampersand x. Then this is p is the pointer, and it assigned address of x. Ampersand operator is used to assign address of x to the p. First, we have our variable x here. Then the program allocates a piece of memory for x like address 0x0012. At that address we store the value 10. Next we have a pointer p whose value is the address of x, which is 0x0012, and there is unique address to p which is 0x0016. So address is always unique to every variable unless it's zero sized type. Understanding this diagram is key to understand the pointers. It is the thing you need to learn to understand the pointers. Let's go to next slide. We have seen the theory and the memory diagram. Now let's jump into the code and see what and how it works. This is where the concept, the address of operator, that is dereferencing, come to life. Let's walk through the code line by line and see exactly what is happening. Let's open the code editor. First, on line 7, we declare regular integer variable x and initialize it with the value 1. Nothing new here. X contain value 1. On the line 8, we have p colon equal to ampersand x. This is our first key operation. The ampersand, that is address of operator, when you put it in front of a variable, it gives you the memory address of that variable. So we are getting the memory address of x and storing it in a new variable p. Now p is a pointer to x, which is 1. So here in it prints 1. So this line prints 1. If we use asterisk symbol to get the value of x. Now, for the most powerful part on line 10, strict p equal to 2, we are using dereference operator. Dereference is this symbol, strict, but this time on the left side of the assignment. This means we are not just reading the value, we are writing to it. This line says go to the memory address that P is pointing to and change the value of that location to 2. Since P points to X, this is the same as changing the value of X itself. To prove this, we'll look at the final line, and we are now printing the value X. And we see it is changed to 2. We can do whatever. This example perfectly demonstrates the power of pointer. They give you a way to modify variable from a distance, which is essential for writing efficient functions that can change their input, as we'll see in the next. Okay, we know how to create pointers and how to get the value they points to, but what about comparing pointers themselves? Can we check if two pointers are same? The answer is yes. In Go, pointers are comparable. This means you can use the double equals or not equal operators to use them. The rule is very straightforward. Two pointers are considered equal if one of two conditions is met. They both points to the exact same variable in memory, or they are both nil, which is the zero value for a pointer, meaning they don't point to anything at all. Let's write the code for more explanation and understanding. Let's see, var x comma y int fmt.print print line ampersand x equal to ampersand y fmt.print line ampersand x equal to ampersand x. So in here, in the first line, we print line, we compare ampersand x equal to ampersand x. We are taking the memory address of x and comparing it to the memory address of x. Since it's the same variable, its address will be same. Of course, they will be always true. And in the second print line, we compare ampersand x equal to ampersand y. Here we are comparing the memory address of x to the address of y, because x and y are two distinct variables. Go has allocated two separate spots in memory for them. Therefore, the addressed are different, and this comparison would be false. And finally, the third print line, we compare ampersand x equal to nil. The nil keyword in Go represents zero value for pointers, slice, maps, and a few other types. For a pointer, nil means it points to nothing, since ampersand x gives us the address of a real existing variable. It is valid memory address and therefore not nil. So this comparison is also false. It's not nil. And run it. The first one for the true because the address is same. Second is the address is different, false. And the third is x is not nil because it's point to 0 as a default value of int. And so that address would be not nil. And let me explain another thing here, that the part the second part of that says that or the both value are nil, then like see this func get nil. This is a simple function which return pointer to string, and I am not returning any string over here. I could return actually a string. And then I could compare like var a comma b gonna equal to nil get nil. Fmt dot println a equal b. This would return something, so it would be false. But if I would do return nil, then that would be true. So this is what I meant, that if they both are nil, like a and b are nil, which is a zero value for a pointer, meaning they don't point to anything at all, then they will be equal. We have seen how to create pointers and pass them into functions, but a very common and powerful pattern in Go is to return pointer from a function. This is often used factory function that creates and initialize a new object for you. Let's explore how this works. The most important concept to understand is this. Every time you call a function, it creates a brand new set of its local variable in memory. Take a look at the function f. It's very simple. Its job is to return a pointer to an integer. Inside the function, it declares a local variable v and sets its value to 10. Then it returns ampersand v, which is memory address of this local variable. Now, if you are coming from a language like C or C++, your alarm bell might be ringing right now. In those languages, returning the address of a local variable is a huge bug because the variable's memory is destroyed as soon as the function exists. But in Go, it is perfectly safe and valid. Go compilers perform something called escape analysis. It detects that you're returning the address of V. So instead of creating V in the temporary function memories, which is the stack, it allows it in a place that will persist after the functions return, like the heap. You don't have to manage any of this. Go handles it for you automatically. This diagram illustrates the core idea. Let's say we call f is a function. For the first time, we create a space in a memory for the function call, and inside that, it creates our variable v with the value 10 at the specific address. Let's say the address is 0xa010. The function then returns this address. Now we make a second call to a function f. Go creates a completely new separate space in a memory for the second call. It creates a new variable v with the value 10, but this time a completely different address. Let's say 0xb004. The key is that each call gets its own fresh variables. This brings us to our main function. Here we have the line printing the boolean that is f. The first function call is equal to second function call, and it returns the pointer, so the answer would be false. Let's break down what happens. The first f calls, it creates a new integer and returns its memory address. And the second function f is called, it creates another new integer and return its memory address. Finally, we compare the two results. We are asking, is the address from the first equal to the address of second? Since each call creates a variable at a distinct address, these two pointers will never be the same, and they will evaluate to false. The answer would be false. Let's see that into the action. Here we created a function as that slides v is equal to 10, returning the address of v, and then we print, is this equal to that? And if we use to check the address, we'll see that it would be false. But if we use if we see that if the value will we will get the value using a strict, which is dereferencing operator, and we dereference that address, then we get the value, and that value is equal to 10. So 10 equal to 10 is the correct answer. So you can see f is 10. Let's see. So address are the different but values are the same. Let's see what's next. Now let's look at the concept called pointer aliasing. It sounds complex, but the idea is simple. You can have multiple pointers that all refer to the exact same variable. This means you can have several different aliases or names that all leads back to the same piece of data in memory. Let's trace what's happening here. First, we create a variable x with a value 10. Next, p equal to ampersand x. We create pointer p that holds the memory address of x. Now, for the key step q equal to p, we are creating a pointer q and aliasing, like assigning it to the value p. Since p value is the address of x, q also holds the address of x. As the diagram shows, both p and q are distinct pointers, but their value are identical. They both point to the same location in the memory of x is stored. Finally, we perform the operation strict q equal to 20. We did reference q and change it to 20 because both p and q points to x. Changing the value through q also changes that p points to. More importantly, it changes the original variable x itself. So when we print the x, it would print 20. Pointer aliasing is powerful because it allows different part of your program to share and modify the same piece of data without needing to copy. Let's let's see it in action. Q new variable which assigned to p, and then change q to 20, which println x, it would result in printing 20, or we can see q plus plus, it would do the same and would print 11.